All right, well, welcome and good afternoon. I'm so happy to be here recording before a live audience. I think CppNorth is a success and I really look forward to the next iteration. Now, some of you might have come here thinking that I would talk about how to progress C++ itself. But that was somebody else's talk. It was taken. So instead, really, I'm here to talk about how not to hang in C++. And that's it, how not to hang. So we're going to talk about progress guarantees. And so what's that? What's a forward progress guarantee? It's kind of a weird term because there's lots of things that the standard guarantees and does not call a guarantee. I actually am not going to explain why this one is called a guarantee. It just is. It's been called like that for a long time. So it's a tradition, I guess. Ideally, a forward progress guarantee would just be this one statement. It would be, your program will not hang, or some version of that. Guarantee. And in a way, even in C++, that is all there is to it. There's a really large subset of C++ where that's just plain true. And a lot of you work within that subset. But it's also C++, so it means there's a bunch of caveats and gotchas. We have a menu of options of progress guarantees. You might think there was just the one. There are three. And in each case, there are some conditions on what's a valid program in order to get that guarantee, which we all know with the endearing term, undefined behavior. So who am I? My name is Olivier Giroux. I'm the chair of SG1. That's the ISO C++ subgroup for concurrency and parallelism, which oversees topics like the forward progress guarantees and the memory model. At the top there is an old picture of SG1, and in it, we can all be seen wondering if this roof will hold us. For my real job, I'm a GPU architect. The photo at the bottom is from the launch of Volta, a GPU that provides independent forward progress guarantees to each of 160,000 threads. And today, I'm a director of GPU platform architecture at Apple, and I'm thinking about what parallelism should be like on efficient devices. I can think about a specific moment that started my interest in forward progress guarantees a little over 10 years ago. We were giving people a programming model with threads and atomics, but programs that you would intuitively expect would work instead would hang. And so you could go on Google or on Stack Overflow, as the case may be, and search for a couple keywords, and what you would get is hit after hit of people who had tried to write one of these intuitive pieces of code and encountered a hang. Now, you know, I'm searching for a lock on CUDA. It's not unreasonable to use a lock on a GPU or other algorithms that aren't lock-free. I would invite everybody to reject that kind of groupthink. Instead, I would say that as a provider of programmable hardware, it's programmable hardware that doesn't live up to the programming system that's unreasonable, not uses of the programming system. Okay, so here's how this talk will work. I will use something called litmus tests, which is something that I'm borrowing from the memory model world, to reveal some facts about C++. None of the programs that I will show are recommended practice. Even the ones that technically work, you probably don't want to write. If a litmus test is a program that has undefined behavior, I will mark it like this. I just don't want anybody grabbing the presentation later on and go, the chair of SG1 wrote this code in a slide deck, it must be good. So if it has a red X, it absolutely categorically does not work. And then in some cases, it does work, but it's a terrible idea. And then I will mark it like this. And then again, like I said, on average, even the other ones that don't have X's are bad. So just don't copy my code. All right, so let's start at the beginning. Let's start with single-threaded code. And here's our first litmus test, and it's a doozy because it represents all single-threaded programs. I have done it My litmus test covers all single-threaded programs from the point of view of somebody who studies forward progress guarantees. So if I don't include these headers, then I can put anything at the anything comment, and that's a single-threaded program. So that's a lot of programs. It's old programs, and it's new programs, yet to be written programs. And now we're going to represent this as a graph of events, which is a thing that I'm going to use elsewhere in the talk. And because this litmus test was very complicated, the graph is also very complicated. We invoke main. Sequenced after that, anything happens. Sequenced after that, we return from main. So it's not the most exciting graph, but they're going to get much more exciting pretty soon. Good news. This program does not have data races, and it does not have any forward progress issues either. That's because it doesn't have any threads in it except for the thread that runs main. But there is some bad news, and the bad news is that microprocessor trends just don't look great for a single-threaded program. Notice the blue part of the chart. Single-threaded programs in absolute terms are just not getting very much faster, even if there's still significant efficiency gains that can be made. The performance has flattened a lot, and that's likely to continue. Meanwhile, the core count, the black at the bottom, is what's increasing quickly, and that's also likely to continue. So if you'll forgive me for glossing over a lot of details, most of the performance is coming from the number of cores, not single-threaded performance, which our single-threaded program can't benefit from. At least not in our code. You can write single-threaded code into the future with parallel cores if you use libraries that are parallelized and accelerated inside of them, and you can continue writing single-threaded code. That can be okay. In fact, even wearing my SG1 chair hat, I would say it is not bad advice to do that and just not use anything in SG1 produces. It's much easier. All right, so now we're going to get out of our system a bunch of ways to use threads wrong. This isn't really talk about how to use threads. It's to talk about forward progress guarantees. I do need to use threads in my litmus tests, so I'm just going to go flip through a whole bunch of litmus tests where I use threads wrong quickly so that we're done with that, and then we can talk about forward progress guarantees. So this program has problems. We'll represent it as a graph. Now it's a much more interesting graph. We invoke main. We run the jthread constructor. It creates another thread which invokes the lambda, which contains the code at A in the previous slide, and that returns. And then back in the main thread, the jthread is destroyed. I'm sorry, the thread is destroyed. Well, that should have said thread. Wow, didn't take long. And then we have the code at B, and then we return. It doesn't have forward progress issues. Instead, the thread version, not jthread, again, has the problem that it has an unjoined and undetached C++11 thread. So it will call terminate at the comment where it says it calls terminate. All right, so that's our first bug. So we'll change it. We'll try to make it better. I said unjoined, undetached. What if we detach it? Well, it no longer terminates. That's great. Instead, it has a data race. The write of data and the read of data are concurrent. And there's plenty of talks out there about data races and proper synchronization, and it's not this one, so we're moving on. Now, there's actually a second problem in this same code, which is that there's a use after free, use after lifetime end on data, which is a capture by reference of this stack variable. This detached thread lives longer than main, so main can return. That detached thread can still try to touch it. In general, detached threads that outlive main are a very, very bad idea. Anything they reference after the return from main, including functions that they call, could no longer exist at that point because of systems with DLLs. So clean shutdown is a really interesting topic just overall. SG1 talks about clean shutdown all the time. But it's not really a forward progress issue, so I'm not going to talk about it right now. Okay, so now I had detached. Let's try join. So I'm going to join it. You'll notice it's not a red X anymore, so it's not UB. But what I just did is I wrote a sequential program using 2 threads to do it. And that's just spectacularly not useful. So here, no computation from main can run concurrently with the computation in the thread, because we joined it right away. And finally, I will use jthread. I also get that if instead of using thread, I use jthread. One thing that is nice and was the goal of defining jthread and adding it in C++20 was so that if you accidentally wrote my first version here, you would get this blocking behavior instead of calling terminate. But still, kind of not useful. Okay, so now finally we're going to mutate it one more time, and we're going to have a version that has some concurrency, and now we're ready to talk about forward progress guarantees. So the first, I mentioned earlier that there's more than one. The first progress guarantee that we're going to talk about is called concurrent forward progress. And that's the guarantee that governs what we informally call full threads. So full threads are std thread, std jthread, and the unnamed thread that runs main. Which is, I made air quotes. And so, and also one more case, any case where the standard says as if in a new thread. That turn of phrase does appear, and SG1 interprets that as meaning literally in a std thread. Okay. All right, so I've used the word concurrent a couple of times, and it's, so I should define it, should give you my definition for it. I define concurrency this way. Concurrent tasks can observe each other's effects. When concurrent programmers do their work, they think in terms of, I do this when that happens. So it's essential that code at this see the effects that preceded that. There's this inherent property of that code, which is that it is about observing effects. And hence, that's my definition. We'll talk about parallelism later. Okay, so here, A and B could observe each other's effects if they tried. For example, if B blocked on an effect that A produces, it would eventually unblock. In this case, we block at the end of B to see the value of data that was produced at A. Okay, so I said it should eventually unblock, but does it, and why? So let's look at the graph for this. So here we have the 2 threads. The most important difference from the previous one, which had bugs, is that there is a synchronizes with edge coming back from the return to the jthread destructor. So A and B are concurrent, but there's no data race on A because we read A at the return and we write the data. We read the data at the return and we write the data at A, and there's a synchronization there. So there's no data race, that's all good. The thread is joined, so there's no use after free. That's also good. Okay, so this graph here, we're gonna start decorating it to apply the various rules that make forward progress tick in C++. Okay, and there's gonna be 3 steps to it. We're gonna need to mark what are the threads of execution. We're gonna identify the abstract machine steps. And then we're going to talk about when the abstract machine has threads take steps. Okay, so let's look at the first decoration of the graph. A thread of control, a thread of execution, is the flow of control that starts from a specific function and includes everything that happens in sequence order after that. So the invocation of main and the invocation of the lambda begin threads of execution. And then we have evaluations of the program that happened after that. Now, even though sequence order in the standard is a partial order, everything that happens in a thread is sequenced after that initial top-level invocation and is sequenced before the terminating action in its execution. Okay, so our program has 2 threads, one for main, one for the jthread. All right, the next step is, no pun intended, is we're going to mark what the steps are. Okay, Okay, so some events in our graph are special. We call them steps. And really what this is just events that matter for the purpose of forward progress guarantees. Obviously, all events in your program matter. But to talk about forward progress, these are the ones that matter. There's 4 kinds. There's termination, like returning from a thread of execution. There's calling an IO function, of which there's none here. There's operating on an atomic or a volatile. Also, there is none here. And synchronization operations. Synchronization operations are those that have in their wording that says synchronizes with or blocks until some condition. And so here we see the JThread constructor is one of them because it synchronizes with the lambda. And the JThread destructor is also one because it calls join, which means that it blocks, and that makes it a step. Now, there's one extra little thing on the graph that you see there. There's a special rule for IO and blocking operations that says that they actually aren't just one step. They stand for an indeterminate number, potentially infinite number of steps until their condition is met. Okay, so now we have one last step. We need to say what takes steps and when. Okay, so for each thread, we'll say that it makes progress when it takes a step, and we'll imbue them with 2 properties. One that says at launch, they're guaranteed to take their first step. They're guaranteed to execute until they hit a step. And second, after they take a step, they're guaranteed to eventually take another step. Okay, so pretty straightforward for threads. Now, there's a little bit of a gotcha. There's a should hanging over all of this. Don't be too worried about that. But in the standard, should means normative encouragement. And yes, it's a great term. And so really it means implementations are not strictly required to ensure that this is true, but they should. Might it be that all C++ programs that block capriciously hang? Yes, technically that could happen. In practice, the reason that the standard has this word there is because it needs to hedge a little bit against you messing with thread priorities, which could create a thread inversion, which makes the implementation of C++ no longer capable of functioning. So that's why there's a should there. In practice, it shouldn't be an issue. Okay, so there we have it, recapped and summarized in plainer English, or denser English anyway. Our concurrent forward progress guarantee, the first of 3. Threads execution eventually take a step, and then they eventually take another step. Clean. Okay, now's a good time to use this lens to take a look at a problem called deadlock. I went back to the program and I added a semaphore. The semaphore is initially unset. There's an operation to set it. The operation to set it is after the destruction of the JThread, and in the JThread, I try to acquire it. So I added synchronization to my program, but I wrote a bug. Let's take a look at the graph version of it. Now in this graph, almost everything is a step. And I have 2 threads. So from the point of view of somebody analyzing forward progress guarantees, everything should be hunky-dory. But you might notice that there's a bit of a problem with the synchronizes with edges in that they cross. They don't just cross, like they cross and form a kind of a loop. There's a circular dependency here. So what's going to happen is that our forward progress guarantee, which we do have, by the way, is going to be used to execute the indeterminate but potentially infinite steps at the blocking operations. We didn't lose our forward progress guarantee, we misspent it. So deadlock is a problem, no question. it is experienced like a lack of progress because it's experienced like a hang, but formally, it's not an issue with your forward progress guarantee. There exists no scheduler, however strong its progress guarantee is, that could execute this code, that can satisfy the circular dependency in this code. So here you see in this diagram a representation of how C++ interprets what you did with your forward progress guarantee. Okay, let's move on to the second forward progress guarantee, which takes a lot more time to elaborate than the concurrent forward progress guarantee. It might be worth noting at the stage that if you were writing in C++ 11, we're done. In C++ 11 or 14, the only progress guarantee that you need to know about is the concurrent forward progress guarantee. Once you get to C++ 17, where we did add parallelism, that's when you start needing the other ones. Okay, so here's my definition of parallelism, especially pure parallelism. You'll see that I'll add a bunch of pragmatic parallelism to it in a second. But just like I defined concurrency as concurrent tasks can observe each other's effects, they're guaranteed to be able to, eventually. For parallel tasks, the lens we want to take is that the default is that we're going to assume the total absence of communication between tasks. So in a way, it's kind of the opposite. And this sort of pure parallelism, this total, when you're totally forbidden from observing effects, is kind of an extreme answer to data races. You can't have any inter-thread conflicts, and you can't have any synchronization whatsoever. So therefore, there are no data races in your program, by fiat. Okay. Now, every real parallel program out there executes on a real computer, and real computers make their effects visible eventually as they execute because they're fundamentally concurrent. So, what would happen if you broke the rules? So you pick up a parallel programming model, but then you write some concurrent code anyway. Well, to a degree, that's going to work. It's going to work because the implementation is not going to be able to hide how it works. And so the concurrency that underpins the parallel programming model shines through, especially in a programming language like C++. And this is highly profitable, so it's profitable for performance. So it's exploited pretty much everywhere that parallelism is used in the field. And we have a name for this, and the name is called discovered concurrency. And it's actually where we're going to start to look at parallel progress, because it's sort of pragmatic version of parallelism, and C++ is nothing if not pragmatic. So we start there. Okay, so we're going to go back to our litmus test, which previously had just one thread, and that was enough to light up the verbiage in C++ that handles concurrent forward progress. But now we're going to have much more than one thread. We're going to create a bunch of threads. Also, if you came late, you need to know that every piece of code in this talk is awful and you should not use this code. I mentioned that. Yeah. Okay, so I have much more than one thread. I have a lot of parallel tasks to do. If you're feeling some anxiety about how large a number of tasks is going to be, that comment there is intended to be an integral constant. If you have some anxiety about how big that number is going to be, you're on the right track. Okay, but now let's draw it. For my graph, I'm going to use 2 because 2 is enough to 1, 2, infinity. 2 is enough to reveal what I want to reveal. But it stands for 200, 2,000, 20,000, anything. Still the same shape of diagram as before. So at this point, we're on our way to talk about parallelism, but we are still looking at concurrent forward progress. For example, a good way to tease out whether you have concurrent forward progress in a parallel-ish framing is to use a standard barrier. So I create a standard barrier with the same number of tasks. I launch all of my threads. In every single thread, I arrive on the barrier and I wait on the barrier, I wait on the completion of the phase of the barrier. Now, since I have concurrent forward progress, this should work. So I'm going to draw it. In each one of my lambdas, I don't invoke main. All right, second slide bug. I don't invoke main. I invoke the lambda. We arrive at the barrier. That is a step because arrive synchronizes with something else. Then I invoke wait, which is also a step because it says that it blocks. And when it unblocks, I will return, which is a step as usual. Now, we don't have a deadlock because I don't have a cycle in my red arrows. So this is good. No deadlock. Okay. All right. Well, how are we doing on our overall goal? We started this journey looking to use many more cores on my piece of silicon whose single-threaded performance is not growing so much. So how are we doing? This is the next few charts are drawn. They're not measurements. I drew them to enhance flavor. Assuming tasks are large, then the overheads of using threads should be low by comparison to the task. It's not going to be 0 though, so if I have a single task, if I'm on the left side, I'm going to be a little bit worse, meaning my time to completion goes up. As I add more of these large tasks going around down the x-axis, then my time to completion relative to having run them all on a single thread goes down because I'm using more cores. Good. So far it's working well. Eventually I'm using all of the cores, and that trend stops improving because now I'm launching more threads than there are cores. I'm adding more overhead, but I'm not improving the rate at which I am doing the work. Again, qualitatively. This looks pretty good for large tasks. Again, if the task is much larger than the cost of creating a thread, for instance. But for small tasks, it's possible that it's just plain worse. It's possible that it starts out terrible, then it improves some. I'm working inefficiently, but I'm still using more cores. So it looks like I'm gaining. But even when I'm using all of the cores, because my tasks are so small, let's say they're 10% the cost of spinning up a thread, then I'm really just spending all my compute resource spinning up threads. And tragically, there's way more parallelism in the world at the small end of the task spectrum. You know, maybe you need to look up 10,000 keys in a map. That's a fairly small task. It's not like I need to render a whole frame or something like that. Okay, so that's too bad. Okay, so we're gonna recurse down into this thing, and we're gonna work on that. We're gonna iterate to get something that's much more efficient. So first we want to amortize it, and so what we're gonna do is we're not gonna launch more threads than we have cores. We're gonna use hardware concurrency as a proxy for that. And we're gonna divvy up the tasks among those threads. Now, this step is very crucial. I am no longer launching a thread per task. And that's when I have taken my journey down to parallel forward progress. So here's my graph. Instead of having one, again, not main, lambda, instead of having one thread of execution per task, I now have hardware concurrency number of them here on my imaginary 2-core processor. And I have more than one piece of parallel work per thread. So what we're going to get is something like this. It has a really big effect on our efficiency. And there's at least 3 things that I want to draw your attention to here on this one. So first, the small tasks keep improving as their number grows. It is still true that if I launch 2 threads for 2 small tasks, and I divvy up my 2 small tasks among the 2 small threads, I'm running very inefficiently. But eventually, I'm running 10,000 small tasks per thread, and the fixed overhead of spinning up the thread gets amortized over all of those tasks. So eventually, it'll reach down to where the large tasks are. Second, you have absolutely noticed the sawtooth shape at this point. So one thing that's interesting that happens in my little scheduler that I wrote, divvying up the tasks, is that when you add, when each thread runs one task, then each thread runs the same amount of work. And it takes the duration of running one task, but across all of the cores. When I add one more task to that, one of the threads is going to run twice as long, and the other threads are still going to run the same amount of time that they did before. So there's a jump up relative to the efficiency of running all of this in a single thread. But then I add more tasks, and I start filling the second phase, and the efficiency improves. Then I open a third phase, and it's inefficient, and then it becomes more efficient again. So you get this sawtooth, but eventually the sawtooth kind of converges, and these two things settle at as if there was no overhead in this whole thing. Good. Oh, and finally, the tails, they don't, in my previous chart, the tail ends of these were trending up because I was spinning up so many threads that eventually my computer is really just computing the thread launch and not really doing work. This is also fixed, and it goes to a flat-ish asymptote. One small vexing thing, not super important, is because of that inefficiency jump, there is this domain where actually oversubscribing the machine with threads would be better than doing this in the large task case where you're just after the jump in the sawtooth. And that is the kind of scheduler effects that makes engineers who work on this, it makes their life very difficult because they go out and they improve the efficiency of the computer on average and on large cases, but then a user files a bug and they say, I used to run lower than the sawtooth and now I run above the sawtooth, and they're pissed, and oh well. Okay, crucial question, do we still have the same progress guarantee as before? And this is kind of foreshadowing, obviously, especially with the big red X there. I'm going to do the same thing. I'm going to create a barrier object, same number of tasks, and I'm going to have where the parallel work was, I'm going to do the barrier arrive and wait. Okay, so it fails. Now, earlier we talked about a deadlock. There's going to be different kinds of failures we're going to experience coming up. So, is this still a deadlock, or is this something new? So I want a quick show of hands. Do you think it's a deadlock?
Yeah. If we count the tasking system in the...
Haha. Okay.
You have to view the whole thing.
Haha, yes. Okay. Okay, all right. And then I'll assume everybody else thinks it's something else. Everyone else thinks it's something else. Okay, so the case for deadlock. I see the threads. I launch them. I see the loop. It's my loop. And I can see the dependencies are not going to be satisfiable. Therefore, I think it's a deadlock. That's the case for deadlock. But we should take a look at what the case for something else could be. Suppose the full threads were actually an implementation of a scheduler. Then that scheduler would have different properties than that of threads. That is, they no longer have this guarantee we had before, which is that after I request the running of these tasks, they're guaranteed to start. Instead, I have a different kind of guarantee. At all times, n of them will eventually start, where n is the number of threads in my scheduler. But they still have the same property that I had before for the final one, which is that as soon as they've taken their first step, they are guaranteed to take more steps. So, that's a deadlock. Indeed. And that one's, let's dive into it because it's all my code. So now the graph has gotten pretty gnarly, but it's important to see that I have, earlier I had in each thread of execution, I had 2 parallel tasks. So now I have expanded my 2 parallel tasks to be an arrive and await each. I took away the main thread because this is gnarly enough as it is. Every arrive needs to synchronize with every wait. And there are several combinations here that are unsatisfiable. So what's going to happen with my forward progress guarantee is just like before. I have it on my threads, and I am going to spend it to execute the imaginary, indeterminate, potentially infinite set of sub-steps inside of the wait steps. Okay. So we've done some amortization. We discovered that it changed what code I could put in my tasks. I still experienced the deadlock because we've not quite created a separation between my code and the scheduler code. Let's keep looking at more problems so that we flesh this out. So one of the problems that we have when we write parallel systems is this problem called tail effects, where the size of each individual task is not necessarily exactly the same. See, if I go and do a find, sometimes I could find it quickly, and sometimes I could find it more slowly, or sometimes I could conclude that the input is trivial, and I'm not going to produce any output, so the task is really, really short. So in real programs, it's not uncommon for tasks to have varying duration. And when you run them on worker threads, let's say here I have 3, you can be unlucky and not have a really perfect distribution of these durations on your different workers. So here I have 3 workers, and the worker at the top got longer tasks. They all got the same number of tasks, by the way, but longer tasks on average than the other 2 workers. So there's 2 ways that you could see this, see the tail in this. Here I emphasize the tail is the worker that sticks out. You could also plot this as a utilization chart. And so at first utilization is perfect, it's 100%, and then utilization falls to 66%, then 33%, and in the utilization chart, that's the tail. Okay, so we're gonna go back and do something else to our litmus test to try to fix that. And here I'm gonna employ a really crude work stealing scheme. And the way that that's going to work is that instead of divvying up the tasks based on a presupposed assignment where every task, where every worker gets specific numbers in the task sequence, now I'm going to have an atomic out in memory, and all of my workers, when they're not doing anything, are going to try to steal a ticket out of that, and that'll be the number of the tasks that they're going to go do, as long as there are any that remain. Okay, so this way, if the parallel work for one of the tasks is really short, then the only thing that happens is that my worker very quickly closes the loop, gets another ticket, and then gets another task. Okay, so in the limit, every thread should run about as long. There can still be a little tail. The longest tail we could have is the length of the single longest task, not the sum of all the longest tasks minus the sum of the shortest tasks. Okay, so here's my graph. Now there's a different amount of work in each thread. We are still going to have the same deadlock as before if my parallel work runs the barrier, but we have taken one teensy tiny step towards understanding what properties my scheduler might have. And one is that actually my scheduler no longer cares how many threads are partaking in the scheme. There could be 1 thread and it steals them all. There could be 1,000 threads that steal. It doesn't matter anymore. These threads could even join or disappear as long as there's always 1 that remains. Okay. Now what I'm going to do is I'm going to take that little bit of scheduler code and I'm going to go hide it in an object off screen that you haven't seen. I'm going to call it my thread pool. Okay. My thread pool has a little queue of tasks that work the same way that the atomic worked. It launches some number of threads. You really don't know how many. And it works with the work stealing scheme that I had before. Okay, let's move on to the next thing. So I've created this thread pool object. And I can instantiate this as often as I want, I guess. So here's another litmus test. I instantiate a thread pool for some outer task, and then inside of my nested task, I also instantiate a thread pool. And now I'm doing some parallel work over a two-dimensional index space. So what I've just done here is I've sort of mashed together the two versions of my efficiency charts. Taken in isolation, each one of my thread pools is working to achieve the amortization on the left, but I've oversubscribed the system because if each thread pool thought it could launch as many threads as cores, now I have many more times as many threads. In fact, in my example, I'll have something like the square, potentially. So in composition, they're achieving the thing on the right. What we need is we need all of the tasks to go and be pooled together so that they all amortize against each other. Okay, great. So I'm going to do that. Instead, I'm going to instantiate just one. I'm going to go make it a singleton, and I'm going to refer to it from now on as the system thread pool. And I express my algorithm the same as before. I go to the system thread pool. I run a set of parallel tasks inside. I recurse. I do this again. And now we're pretty efficient. Okay. Well, now we're ready for the final problem that we need to solve to understand parallel progress. And that problem is that the tasks can starve each other. All right, now I'm going to write another program that you should not write, and the reason is I want it to fail spectacularly. Okay, so now I've mashed together two versions of the litmuses that we had in this section. I create as many threads as tasks. Okay, so I'm back to that one. And I give to the shared thread pool one task per task. All I'm doing is sort of doing the trick of running a single-threaded program with multiple threads. I'm doing it again. I'm using the thread pool to run just one task per thread. And then I make it run, I make it arrive on a barrier. If I wasn't using the thread pool at all, this would work. We saw a version of the slide earlier, and it did work. But now I'm just wrapping it and putting it in the thread pool like this. If I had instantiated a local thread pool inside of my thread, what we just eliminated in the last section, this would work. But this here is not going to work. And the reason for that is that the system thread pool, the shared thread pool, its guarantee for how many tasks it is going to start is not on the per sets of tasks given to it, it's per system. If I spin up 24 threads on an 8-core system, let's go back to the previous example. If I spin up 24 threads on an 8-core system and my shared thread pool spins up 8 threads because it looked at hardware concurrency, then I arrive and I submit 24 sets of tasks that are each a singleton of one task. It will pick 8 of them to run, not 24. Okay. So my guarantee now on a per set of tasks basis is not at least one task starts, it's at least 0 tasks start. Okay, so enter one last thing, and in vernacular, we call it boost blocking. In C++, we call it blocking with forward progress delegation. And here's how it works. So first, we're going to return a way to block on a set of parallel tasks that were submitted to the thread pool. So we're going to return some sort of a handle that says, yep, I've taken receipt of this bunch of tasks from you. And then, when I block on that, I have an opportunity to take an action. And there are a couple of actions that we could take. This set of 3 here is absolutely not comprehensive. It's just the 3 I came up with for this slide. I could react, note that they're not running, then begin a sort of a preemptive scheme that preempts some of the stuff off of the thread pool, then launches some more threads. Or I could literally just throw more threads, at least one thread per set. If I have one thread per set in the thread pool, then each set will get at least one task is guaranteed to start. Or finally, and this is a clever thing, I could make the blocking thread partake in the work stealing scheme. I could make the blocking function on this little handle that was returned contain within it the same code that a worker thread uses to steal work from the pool, thereby when a parent thread wants to wait on its child work, the parent's own thread becomes an execution resource that the child work can run in. Okay, so now the effect on my litmus is not huge because you're not seeing what happened to my thread pool. My thread pool header like tripled in size when I did this. In my code, I just capture some sort of a returned handle from submitting work to the thread pool, and then later I say, drain that, block, wait, whatever. And within that function, it does the work stealing, and now this will work. Because if I launch 24 threads, each one submits a task to the thread pool that has only 8 threads. 8 of them will actually run block. Then the 16 other ones, their parent threads, when they arrive to block, will donate themselves to go run this work. And now my thread pool will, at least temporarily, appear to have 24 threads in it. Actually, it'll probably appear to have 32, and 8 of them are waiting on the 8 that ran but not complete. But anyway. Okay. So let's go back to our case for something else. And it adds this clarification. If a set of tasks is blocked on, then at least one of those tasks that hasn't completed eventually starts. And that's what gives us parallel forward progress. Under parallel forward progress, threads of execution don't eventually take their first step. If they're blocked on with forward progress delegation, then at least one of them takes a step at all times. And then whichever one has taken a step eventually takes another step until it completes. And it will not surprise you that that's the progress guarantee provided by parallel algorithms. And here I'll write just an example parallel algorithm, a really crappy my for each, and my for each just passes the iterators in lambda down to my thread pool. Right, so actually let me just talk to it a little bit, right? So my index range is going to be the distance between the first 2 iterators. I then run your lambda on an iterator advanced from the beginning up to the index that I got from my thread pool. So if you send me a range of 24, I give the thread pool 24 tasks. Each one invokes this lambda. They will be receiving their task ID 0 to 23. So therefore, I invoke your lambda with the iterator advanced with by next by an index, which is 0 to 23. And the parallel algorithms that are in C++ 17 work essentially like this. They do submit parallel work with parallel forward progress guarantees and immediately blocks on it inside. These algorithms are not asynchronous. They don't expose. They don't return to you a handle to block on the parallel algorithm. They block internally. It's as if they've invoked that drain on the handle that was returned. And that means, by the same fact, that they provide blocking with forward progress delegation to those parallel forward progress tasks. Okay. And now, what happens if I write this? I'm back to using a barrier. We should expect that it does not work. In fact, it should expect that there's a red X on this thing. Now let's ask ourselves, is this a deadlock? Well, it's a lot less clear than it was before. If we look at the case for deadlock, we don't see the threads. They're owned by the system. They're owned by the scheduler that runs the tasks. We don't see anything about how the tasks are assigned to whatever will be the underlying execution resources that execute that. we don't see the dependencies that are definitionally unsatisfiable. And the reason for that is, conceivably, a scheduler could run all of these tasks concurrently. We just don't know that this one does. So we don't really know. We don't see enough to confidently conclude that it's a deadlock. It could be something else, though. If we view our tasks as the thread of execution, if we view the threads that are owned by the thread pool as the scheduler, we imagine that the scheduler, we know that the scheduler has these properties we've identified step by step coming here, then I would argue that this is something else, and that's called a live lock. And a live lock is a program that requires stronger progress guarantees than a scheduler provides for any pairing of program and scheduler. Okay, so I can still write a deadlock with parallel progress, still possible. I just need to not exceed the progress guarantees of the parallel progress scheduler, which really boil down to it guarantees that we'll run one task. So I could write a deadlock, but I would have to do something very contrived like I did before of running one parallel task at a time and try to synchronize with that. Okay, so not every hang is a deadlock. Some of them are live locks. Okay, so this last one was a lot of work, and we have concurrent and parallel progress done. There's one more, and actually this one more is going to be really quick. It's called weakly parallel, and I'm going to go back to my definition from earlier. Parallel tasks never observe each other's effects, and this is the pure parallelism definition, meaning think of it as you are not allowed to use discovered concurrency. Under pure parallelism, you can't communicate at all. So if you can't communicate at all, what kind of forward progress guarantee do you really have? It's a bit like a tree that falls in the forest and no one sees it. So we do have just the one more, and this one puts into the standard a way to write code that essentially makes no useful assumption of progress. Your threads of execution don't take a first step. If they're blocked on, one of them will take a step at all times. But instead of each one that took a step is guaranteed to take another step, this is completely reset at every step. An arbitrary one could take a step. And that allows, for example, in execution, suppose that I had these two threads and I had given them weakly parallel forward progress. So let's say that I said that the main and the lambda were part of a weakly parallel progress scheduler. That scheduler would be allowed to always choose the infinite sequence of steps in the blocking of JThread and never execute anything in the lambda. Okay, but they're not supposed to synchronize, they're not supposed to do that, and therefore it's forbidden from the programming model level. Okay, so why bother? So we had concurrent forward progress, which is what you get from full threads. We have parallel forward progress, which is what you get from reasonably running parallel algorithms on thread pools. I said earlier C++ is a very pragmatic language, therefore we started with the pragmatic version of parallelism. Why still bother with pure parallelism? Why put anything in C++ that is for pure parallelism? And the reason for that is diversity of implementation. C++ often will have bare bones options. For example, memory order relaxed is a thing you should probably not use. And memory order relaxed has some benefits on some pieces of hardware, and that's why it's there. This is actually similar. For truly independent work, earlier I used an example, you want to look up 10,000 keys in a std map. Well, if you want to look up 10,000 keys in the std map using the const member function find, nothing about that will have read-write conflicts between the tasks. That is pure parallel work. It's not trivial work in the sense of am I just adding 1,000 numbers with another 1,000 numbers. It's slightly more elaborate than that. But it's still pure parallel work. There's no communication between these tasks. Okay, so we should be able to make implementations that are allowed to go much further in optimizations if we have a guarantee that there can't be any communication. For example, vectorization. There's a pretty cool compiler out there called ISPC that will compile code that has the same sort of semantic contract as parallel algorithms. You give it an index space of iterations, but instead of running it on a thread pool or running it in some sequence in the same thread, what it will do is it will run the different iterations in that index space on vector lanes. But it can't handle things like giving you a forward progress guarantee on the per lane level, because that's just not how the hardware works. And for another example, GPUs. Many GPUs don't conform to parallel forward progress, but they are capable of conforming to weakly parallel forward progress for the same reason as the SIMD case. Okay. All right, so let's just take a quick look at how that gets spelled into C++, parallel and weakly parallel. You get it by using parallel algorithms like for each, and you pass in an execution policy like std execution par or std execution par on seek. Std execution par gets parallel forward progress guarantees. Std execution par on seek gets weakly parallel forward progress guarantees. Okay, so for example, here I'm using par, which gives me parallel, and that allows me to do things like even take a lock. See, in my lambda down here, I'm taking a mutex. A mutex does not require the guarantee that you eventually start each single task. The guarantee that it requires is that any task that has started and therefore potentially acquired the lock keeps taking steps so that eventually that critical section is known to finish, so that anybody else who is blocking on the lock will eventually be unblocked. So parallel forward progress, you can't use barrier, as I've pointed out multiple times now, but you can use a lot of things like mutexes. Now you can't do that in weakly parallel forward progress, obviously, because that is a conflict between threads and that's disallowed. Actually, there's going to be two reasons. I'm going to need to harp a little bit more on that. There's going to be two reasons why the lock is not allowed if it was par and seek. One of those reasons is that you do not have an independent forward progress guarantee for any thread that took the lock. There's no guarantee that we will execute the steps that cause it to eventually release the lock. We could just capriciously always choose to only execute steps in threads that are blocked. So that's one of the reasons. And I will talk about a second reason pretty soon. Okay. Now I said also, you could still do really interesting things with weakly parallel. Here I'm doing this example of looking keys up in a map. Nothing wrong with this one. All right. Now, a little bit of a head scratcher. I think this one is a bit confusing. Under par unseek, I cannot even use atomics. And that was not entirely intended, I think, by SG1. Why? So assume that my atomic here is lock-free. I'm going to assume that std atomic int is always lock-free. So if it's lock-free, presumably it's not making strong assumptions about my forward progress guarantee. So under par unseek, I don't have the same kind of guarantee as par, but I'm not assuming it because I'm not using a non-lock-free atomic. Good, good. The issue is that par unseek has a one more thing. Par unseek is not just that it has weakly parallel progress, it also allows execution unsequenced within a thread. That's the unseek part of par unseek. And in C++, the UB for unsequenced, for conflicting read-write effects that are unsequenced, has much higher priority in deciding whether it's UB or not than atomicity. In the atomics clause, it says you don't have a data race if you have atomic operations that are potentially concurrent. That only dissolves the UB that could come from having a data race. It doesn't dissolve the UB that's associated with unsequenced read-write conflicts being undefined. Okay, so we can't use atomics in here. I have a couple of these loose ends that I would like to point out. Basically, various bits and pieces of the standard that interact in interesting ways with the forward progress guarantees, or things that are kind of underspecified. And I can't really quite tell you what the meaning is, as G1 has a sense shared among the members of what it means, but it's not really written down. Okay, so let's dive into that. First, I want to tell you about my favorite undefined behavior in C++. I'm sure everyone has one. This one, I unironically love it, meaning I love it, I don't want it to go away. Don't write a paper to take it away. Okay, so some of you might know that C++ forbids infinite loops without side effects. And that's often cited as the permission for C++ compilers to delete these loops, these empty loops. But what it actually says, it doesn't say C++ compilers can delete empty loops. That's not what it says. What it says is that implementations can assume that threads eventually execute something. That's a step. It's not phrased in terms of loops. It's phrased in terms of threads, steps, and eventuality. So what it says is that the box there, the A box, the one that's not a step, it says it's finite. Every one of these boxes that don't have the blocking loop are guaranteed to be finite. No proof required. You ingest the program from source, as a compiler, you know this, no proof required. It's finite. Okay, so what you could do then is you can think of threads as sequences of threadlets that end in a step. So I'm going to take every execution of a thread, and I'm going to say, well, it eventually executes a step. Simple threads that don't synchronize only have the initial invocation and the return, and they're made of a single threadlet that ends with a single step, and it's the return. But more complicated threads begin, eventually execute a first step, having done a finite amount of work between launch and that point. Then execute another finite amount of work and perform a second step, and so on until they return. So here I've diced up my threads into 5 threadlets, each one of which contains a proof de jure that it is finite. Okay, so I can build a scheduler, a very low-level scheduler potentially, that works with this information. All right, so what could we do with that? So I could visit my threadlets. I could make a system. For example, I could make a fiber-based system or a green thread-based system that switches fibers at events that are steps. And I could visit them in that particular order, for example. I could go 1, 2, then 3, then 4, or I could do 1, 3, then 2, then 3 prime, then 4. Those are the 2 valid orders of sequencing these threadlets. And that consequence is super cool. I'm sorry I'm nerding out about a thing here. It's super cool because it means that C++ can be implemented with non-preemptive schedulers, provided the schedulers know where the steps are. Super cool. Okay. Next, I'd like to talk about memory model impacts. It's useful to think of the forward progress guarantees and the memory model as being two completely separate topics, but they sort of touch each other in multiple places. So let's quickly inventory those places. Well, first, progress is both fundamentally a cause and a solution to the data races. When I created threads that potentially execute concurrently, I created the opportunity for me to have data races. I resolve those data races by having synchronization that blocks until the effects are separated by a synchronizes with edge, right? And that's using the progress guarantee to eliminate that race. So there is this sort of yin and yang relationship here. Next, in the atomic clause, it talks about eventuality, that effects on atomics are eventually made visible to other threads. In the progress clause, it also talks about eventuality, that threads eventually take a step. These two eventualities are the same eventuality. You could not prove that you have one but not the other. You always prove that you either conclude you have neither, or you conclude you have both. And here's why. How do I prove that atomics are eventually made visible? Well, I create two threads, and they try to observe each other's effects. In order for the two threads to have a reasonable basis to expect that they can observe each other's effects, they have to have a forward progress guarantee. Conversely, if I want to check if my forward progress guarantee has been violated, then the effects have to eventually be made visible, and those effects are on atomics. So if I made a computer, for example, that I swear to God it takes steps forever, but it has an infinitely sized cache that never writes back, then you would be in your right to judge that actually my forward progress guarantee is not working, right? And the inverse is also true. Okay, the next one is a little bit of a bigger thing to get into. Roach motels should not be a problem. And I'm going to explain this one. What do memory model people mean when they talk about roach motels? So here I'm going to quote Wikipedia. There's this brand of cockroach traps called Roach Motel, and they have this really cool tagline where they say, roaches check in, but they don't check out. Yeah. Yes, they check out in the trap, yes. Okay. So acquire and release operations in C++, they allow other surrounding operations to be reordered with them in one direction. Here I'm using semaphores to make everything look simple. This applies to atomics. It applies to every synchronization primitive. I can move things over synchronization, but only in the direction that's safe, not the direction that's unsafe. So I can move the statement at A inside of a critical section. I can move the statement at C inside of a critical section, so below an acquire or above a release, but I cannot do the reverse. I cannot move something that's inside the critical section above an acquire or below a release. Okay? Therefore, the analogy is these evaluations, computations, these events, they can check in, but they can't check out. Okay. Now, let's imagine this program. It's kind of backwards. Here, I have two semaphores, they're unset. I have two threads, main and my J thread. What they do is they start by setting one of the semaphores and waiting on the other one. And again, there's an infinite series of evaluations inside of the acquire here. So let's take a look at the graph for that. It should look like this. There's no deadlock here. My synchronizes with edges. They cross, but they don't form a cycle. This is fine. And now I'm going to apply a surprising roach motel. I'm going to move something above an acquire and something below a release that's not forbidden from moving. What I'm going to do is I'm going to swap them. See, I'm going to go back to the previous one. I can move things below an acquire, including a release, and I can move things above a release, including an acquire. So I could do that. Can I do that? Well, if I do that, then there's a problem. If I do that, then I have a deadlock. I have my synchronizes with, and now not only do they cross, but they do form a cycle, and what's going to happen to my progress guarantee is the same thing as before. I'm going to be spending it running these blocking loops. This should not be possible. I know, at least as part of the implementers that I have worked for, inside, we talk to each other about how this is forbidden in our implementations, and we should never do that. It's unreasonable. However, the standard doesn't really speak to that. It's kind of an implementer contract. And it's sort of missing what I call optimize as if isolated for a finite time. Like you should never be able to move, fuse, atomic operations, if you would move or fuse an infinite number of them potentially. So what should stop the code motion, in the previous slide, I'm going to go back, is the little indeterminate, potentially infinite amount of steps in the acquire. That should not be allowed to move over or release. Okay. All right. We're almost there. So let's talk about lock freedom briefly. So lock freedom certainly starts by not using locks. I had an interesting exchange a few years ago where somebody thought any program that does not include mutex is lock-free by definition. And yes, and there's a few problems with that. So you also need to use atomics that are lock-free. But then finally, you also need to not make any progress assumptions. Like you need all three of these things. If you use lock-free atomics, but you write a loop that assumes forward progress, then you have a problem. Okay, so here's a program that uses lock-free atomics. Does this program complete? It should. Well, we have this misnomer in C++. We misnamed lock-free, and there's a little note. I'm sorry that I cut and pasted from the standard. Let's look at the top box. There's this little note that says describing lock-free in C++ actually says this property is known as obstruction-free. And if you look that up, obstruction-free requires a thing called a fair scheduler, and that's the second box. And what a fair scheduler needs to ensure is that eventually a thread will execute this operation while no other thread is attempting to do the same for a long enough period of time. And then it tells you that you should have a backoff to ensure this property. And C++ says absolutely nothing about what would be a program where you would be expected to have a backoff. It told you, I have this thing called lock-free. It's not lock-free, it's obstruction-free. It sent you to go do your homework, learn what that is, learn that you needed a backoff, and then told you nothing about what to do. So again, this is one of these, like the should earlier. Might any reasonable program using lock-free atomics in fact hang and never complete? Yes. And in practice, they shouldn't. Okay, we touched on atomics not being allowed under power on seek. So for example, that's not allowed. We could ask though, having just talked about lock-free atomics not being lock-free, we could ask, okay, could we relax this? Could we allow lock-free atomics? SG once talked about that. It currently does not. That's something worth considering. Or maybe we could have a par weak, which has weekly parallel forward progress without having unsequenced, just not activating the unsequenced UB on us, and then we could use lock-free code. Speaking of which, what about magic statics in par on seek? So C++ today, I think, actually fairly clearly says that this should work because there is no place in it where it ever talks about it maybe not working. However, the completely equivalent code using call once is forbidden. So I'm a little bit confused about whether magic statics are allowed under par and seek, and maybe they shouldn't be. Okay. And then for much of this discussion that we had, there was this assumption that threads of execution can be something a little bit different from a full thread. Now, the exact properties of threads of execution are not super documented. For example, what should happen under par and seek if I grab the thread ID? So this is, it's a weird transform. I'm using this transform just to read the thread IDs and send them out. Okay, that's all I'm doing with it. I can read thread ID inside of par and seek. Am I going to have, how many of my parallel tasks will conclude they have the same thread ID at the same time? Or what about TLS? Or, and obviously you shouldn't do that, but what if you tried to figure out what the stack addresses were? And this is one where I am personally actually a little bit on the fence about whether atomics should be allowed under par and seek. Because today, there's no useful way to exchange a stack address between two tasks that would be given to par and seek. But if I give you lock-free atomics, you could give someone else an address on your stack. And I said earlier that par and seek is intended for ultimate implementation diversity, including SIMD and GPUs. And this exchanging of stack addresses extremely does not work in these two systems. So here there be dragons as we relax the constraints. Okay, so finally, just a quick word about the future. Earlier, I showed my example parallel algorithm, and I said it sends this to the thread pool and immediately blocks on it, therefore immediately blocking with forward progress delegation. Everyone thinks, actually, that it would be nice to have a synchronous version of these algorithms. So, maybe we could return some sort of a waitable type out of this, and then you could compose parallel algorithms with asynchronous algorithms, and that's called senders and receivers, and certainly that's a very much longer talk. This being said, there's no need to wait 4 more years for that because we're talking about C++ 26 at this point for senders and receivers. There's a lot of really good value in the parallel algorithms that are in C++ 17 now. So I would argue parallelism should be normal now. Normalize parallelism. While minding the progress guarantee, so your program will not hang. Thank you.